Let us continue the presentation of CSEC Practice Paper 2 with Part B, another 15 problems, going from problem number 16 to problem number 30. The shaded part of the Venn diagram represents which one of these options? The shaded part of the Venn diagram is the region that is shared between the two sets. That portion is called the intersection. The symbol for intersection is something that shapes like an N or an upside down U. Right. The correct answer is option D, because in option D we have this same intersection sign, and that is represented by the shaded region that we have here. It is shared between set P and set Q. It is the intersection of the two sets, and of course option D is correct. Another of the symbols used is union. The union of sets is the set that contains all of the elements that are in the sets taken together. That's what the union is. All of the elements taken together, and that is the symbol. So after solving the problem, we are not taking anything for granted. We are just making mention of some of the symbols that are used in set theory, and no doubt we'll see a lot of them coming out when we are solving a lot of other problems. The other symbol is complement, and it refers to the elements that are not in a particular set or combination of sets. Therefore, the complement of set P will be the set that contains all of the elements that are in the diagram, in the Venn diagram, or all of the elements that we are speaking about in a particular situation that are not in set P. The equation of the line that passes through the point 0, 2 and has gradient 1/3 is which one of these? The examiners expect us to solve this problem in a matter of seconds, but that is dependent on us taking note of one important fact. When M is the gradient and C is the y-intercept, and the y-intercept, of course, is where the line crosses the y-axis. So where C is the y-intercept and M is the gradient, the general equation of a straight line is given as follows. Y is equal to mx plus c. M is the gradient and c is the constant, the y-intercept, where the line crosses the y-axis. There are formulae including y is equal to mx plus c that may be used in solving the problem, but it will take a longer time if we do not realize that the point given is actually the y-intercept. So we have many different ways in which we can determine the equation of a straight line. In this particular case, we will take an unnecessarily long time to solve the problem if we do not realize that the point that is given right there is actually the y-intercept. And that y-intercept, of course, is 0, 2. That same point that we have. 0, 2 is a point that is located on the y-axis because its x-ordinate is equal to 0. The y-intercept is therefore equal to 2. Alright, so it crosses the y-axis at 2. The x-ordinate is equal to 0. Any point that has x-ordinate equal to 0 is a point that is on the y-axis. So we have the y-intercept right there. All we need to do is to substitute m is equal to 1/3 and c is equal to 2 into the equation. So we have the equation right here, and m is 1/3, c is 2, and we are done. Right, so if we could have seen that we could have just said, okay, yes, we are sure the line has equation y is equal to 1/3 x plus 2. The correct answer is option D. And if we did not realize that, then we could use some other method to find the equation of the line that would be a little more time consuming. There we have option D. On the next slide, we will see how two other methods using two different formulae may be used to determine the equation of the straight line. Although each one is not very time consuming, unnecessary time will be wasted if we use either of them rather than writing down the equation of the straight line as we have done. As we have seen before, the key to solving the problem in a few seconds is to realize that the point that was given is actually the y-intercept. We have two formulae. Y minus y1 is equal to gradient x minus x1, this first one that we have here, and we have y is equal to mx plus c, the general form. But we are going to use it in a different way from what we used on the previous slide. The one that we have used on the previous slide is dependent on the fact that we realize immediately that the point that was given is actually the y-intercept. Now we have the point which is 0, 2, and we have the gradient which is 1/3. So we have y minus y1, which is y minus the y-ordinate, is equal to the gradient multiplied by x minus the x-ordinate. What do? In the place of the y-ordinate, we put the value 2. In the case of the x-ordinate, we put the value 0. And of course, no doubt, we have 1/3 will replace the gradient m right there. Making the substitution. After making the substitution, we will proceed to simplify. So we will have y minus 2 is equal to 1/3 x minus 0. Of course, we could have neglected the 0. So we have y minus 2 is equal to 1/3 x minus 0, and we have y minus 2, we have neglected the 0 that we have right here, to the effect that we have just 1/3 of x, and no doubt we can just finish up by transposing this negative 2 to the other side, in which we will have y is equal to 1/3 x plus 2, and of course it is in the general form. Now we will make use of y is equal to mx plus c, and usually the first thing we do is try to find the value of c by using the point that we have here. So by substituting, we have y, which is 2, we have 2 there, m is 1/3, we'll place the 1/3 there, and of course x is 0 right there. We do not know the value of c. We are attempting to find the value of c. So we do our substitution. Of course, anything multiplied by 0 is 0. So all we will have is 2 is equal to 0 plus c. Of course, 2 is equal to c. The general form will be, of course, y is equal to mx plus c. We have m is 1/3 and c is 2. So we will replace m by 1/3 and c by 2. And we have the same thing. Y is equal to 1/3 x plus 2. And of course, as we have demonstrated by going through especially this process, that the solution could have taken a much shorter time if we realize that the point that is given is actually on the y-axis, to the effect that the y-ordinate is going to be identically equal to the y-intercept. the water authority charges $10 per month for the meter rent and $2.50 for the first 1,000 liters. So we have $2.50 for the first 1,000 liters. Then 10 cents for each additional 100 liters. What is the total bill for 2,500 liters used in 1 month? One of the greatest problems that we will have solving this one is some students will realize that we are using 10 cents here, and they will not realize that the 10 cents is for each additional 100 liters, and they use it 10 cents for each additional liter, and we will have a serious problem right there. In solving problems like these, one thing that candidates usually neglect is the monthly fee. So let us put that down first. So students generally forget about the monthly fee when solving problems like these. So we'll just put that down first. And sometimes the bill is over 2 months period, and they have neglected the fact that it is over 2 months period, and sometimes they don't even include the monthly rental. And if they include it, sometimes they include only one. In this particular problem, we are just being asked for a single one. Therefore, we have no problem progressing with that. So we will put the rental down first. So let us make note of the total amount of water used. We have it right there, 2,500 liters. The first 1,000 liters cost $2.50. Right. 1,000 liters, $2.50. We'll take note of that also. But what is going to happen is that we are going to take out this 1,000 liters. So the remainder will be 10 cents for each 100 liters. So in order to find the remainder, we will subtract first. Subtract 1,000 from 2,500. There we have it. 1,500 liters. We will next divide the remainder by 100. Do not forget that the next rate is for every 100 liters. Not for every liter, for every 100 liters. So we divide by 100 and we'll get 15. Finally, apply the 10 cents or $0.1. So we are multiplying that by 10 cents and we will get $1.50. So what remains, which is 15,000 liters, we need to divide by 100 because we are applying the rate to each 100 liters. Add all of the monies together. So we are going to find the total. We have 10 here, 2.5 and 1.5. 2.5 plus 1.5 is 4. So 4 plus 10, 14. And that's all there is to it. The correct answer is option C. Triangle LMN is rotated anticlockwise about L through 90 degrees. Which of the following is its likely image? In solving problems in mathematics in particular and life in general, it is wise to use things that are convenient to you. We may therefore consider the horizontal line LN in the original object because it is easy to see the result of rotating it through 90 degrees anticlockwise about L. So we are going to use this convenient line LN because it is horizontal. So if we rotate it 90 degrees anti-clockwise, it will be vertical. So we are making use of that fact. That simplifies our problem. After rotating through 90 degrees anti-clockwise about L, it will be vertically above its initial position, like so. Right, and there we will have the image N prime. Going in a clockwise direction, the point M will be ahead of the line N. Its position relative to the line N will be right there. So notice that M is above Ln. So when we rotate, M will still be ahead of Ln or Ln prime. So that is where M will be. So that is our location of M, or relative position of M. Of course, the position of M relative to the line Ln. Not necessarily exactly, but a good idea. And in solving this problem, or problem like these, most times we do not need an exact, pinpoint, accurate position. The one in which the relative positions of a line and the points are similar to our little demonstration is option B. So the one in which the position of the line here relative to the point is similar, the one that is similar to this is our correct answer, and that one is option B. And of course we can complete the diagram and see it kind of looks like it. It is not necessary that it looks exactly like it. We will do with a very close approximation. That is all that is needed in this particular case. Same problem. What do we do? Apart from that, we may take a look at what a real rotation through 90 degrees anticlockwise about L will actually yield. So apart from making an approximation and making use of the horizontal line that is convenient, we will actually do the 90 degrees rotation. Like that, all the way to 90 degrees. And that is what it looks like. Now that you have seen, you have believed. Blessed are those who, in the weight of adequate evidence, have believed. Right? I will not bless those who have not seen and yet believe. The person who makes use of evidence in order to come to a conclusion is more blessed than the one that is making a blind guess. So we see that it looks like that one. So we know that our conclusion in the first instance was correct. Now we have a linear equation and we need to solve for x. Let us rewrite the original equation. Just write it there. We're going to solve it. In solving an equation for x, we need to eliminate every number from the same side as x, beginning with the one that is least related to x. 6 is added to the side that contains x. Let us subtract 6 from both sides. The result will be that 6 will be completely eliminated from the left hand side, and on the right hand side 7 minus 6 is equal to 1. So we need to eliminate the one that is least related to the x, which is 6, and we have it added here. We subtract 6 from both sides. 6 is eliminated from this side completely when we subtract 6 from this side. When we subtract 6 from the other side, 7 minus 6 is equal to 1. So 2x is equal to 1. On the left hand side, we are multiplying by 2. That is what 2x means. 2x is equal to 2 times x. We will therefore eliminate 2 by dividing by 2 on the left hand side. When we have an equation it needs to be balanced. So what we do to one side, we need to do to the other. So we will divide both sides by 2. And what will happen? The result will be that 2 will be totally eliminated from the left-hand side, and 1 on the right-hand side will be divided by 2. So, need to get rid of this 2, we divide by 2. Cannot do that alone, we need to divide by 2 on both sides in order to keep the equation balanced. So, divide by 2 here we get x, divide by 2 here we get half. So, eventually, x is equal to half, and that is our option C. The correct answer is therefore option C. How much more interest would a fixed deposit of $1,000 earn in 1975 than in 1976? And we have our rate of fixed deposit right here. So how much more will one cost, or will one earn more than the other? On seeing this problem, one may say, I know what to do. I will find 7.8% of $1,000, then find 7.5% of $1,000, and finally subtract the two results. This is very good, but it shows a bit more common sense to subtract the two percentages, then find 0.3% of $1,000. So subtract the two percentages instead. We have 0.3%. Now find 0.3% of $1,000. Let us do it mentally. 0.3% is 0.3 divided by 100. We will reduce that by 2 places of decimal, and that will give 0.003. Right. Multiply by 1,000. So 0.3% is 0.003. And that we are multiplying by 1,000 because we are finding 3% of 1,000. Right. Multiply the numbers as if there is no decimal place. That is what we do when we are multiplying with decimal numbers. We just multiply as if there is no decimal place. And that is what we would have received. So we'll say 3 multiplied by 1,000 is equal to 3,000. Then the original product has 3 decimal places. Since the original product has 3 decimal places, the answer should have the same number of decimal places. 3 decimal places in the original product, 3 decimal places in the answer. Right. So those are negligible trailing zeros. So the answer is $3, and that is represented by option B. Same problem, different approach. On the other hand, we may demonstrate a bit less imagination by finding the different percentages of the principal and subtract the results. There we have them. You are dividing by 100 and multiplying by 1,000. It should not be too strange that the answer should have 1 less decimal place. So, in multiplying by 1,000 and dividing by 100, the overall effect is multiplying by 10. When we multiply by 10, the number of decimal places will be reduced by 1. So, instead of 7.8, we will have 78. And on the other side, we will have 75. Each number had 1 decimal place. 1 less means that the result will not have any decimal place, as we have shown. We may then find the difference between the two numbers. Of course, 1 less decimal place than 7.8 will be 78, and of course 1 decimal place less than 7.5 will be 75. Then we subtract, and the result is $3. as we have done before. Luckily, the principal was not an awkward number like $897. That would have caused the calculation to be less desirable. The principal is a friendly number, which is $1,000. This caused a lack of imagination to have milder consequences than normal. Right? So when people demonstrate a lack of imagination doing things, they generally have a much harder time accomplishing what they are trying to accomplish. When they use some imagination in what they are doing, it is less time consuming, it is with less hassle, and generally people who are prepared to think will have life a lot easier than those who don't. PQRS is a rectangle in which PQ is equal to 8 centimeters and PS is equal to 6 centimeters. QSTU is a square. The area of QSTU is, that is what we are trying to find, the area of QSTU. Right. Any mathematician that is worth his salt will be able to look at it and tell that the correct answer is option D, 100 centimeters squared. Why? The greatest reason is that the distractors are very poor. QSTU is a square. This means that its length and width are equal. The only answer among the option that is a square number is 100 centimeters squared. So we know that QSTU is a square. Therefore, in finding the area, we must square the length of one side. Looking over here, we realize that 100 is the only square number. Therefore, it is the only possible answer. All of the angles in a rectangle are right angles. Half of that rectangle will be a right angled triangle. So we are attempting to use another method in finding the area of QSTU. There we have it. We are attempting to use the fact that since PQRS is a rectangle, that half of it will be a right angled triangle. Then we can use Pythagoras Theorem to find the length of this side. If we find the length of this side, which is the hypotenuse of this right angled triangle, we would have found the length of one side of the square. Then we multiply by itself and we will find the area of the square. The hypotenuse of the right angled triangle is one side of the square. Right, so the hypotenuse of this right angled triangle is one side of the square. We may use Pythagoras Theorem to find its length. So let us use Pythagoras Theorem. We have the formula for it right there. All we need to do is substitute the values 6 and 8. So we have a representation, algebraic representation of Pythagoras Theorem right there. All we need to do is substitute the values. 6 squared plus 8 squared. Of course, 6 squared is 36. 8 squared is equal to 64. 36 plus 64 is 100. The square root of 100 is 10. So we have the length of that side of the square is 10 centimeters. The length and width of the square are equal. The area of the square is 10 squared, or 10 multiplied by 10, and that gives 100 centimeters squared. And that is what we have right here. Good. Another candidate may look at this problem and without taking note that 100 is the only square number here, still will be able to solve this problem in a matter of seconds. Let us say that the distractors were good and the answer could not have been identified by the specified uniqueness. It still would not have been very difficult to determine the answer if we are quite familiar with right-angled triangles. So this is unique and we are able to identify it is unique. It's the only square number there, and we could just look at that and know that that should be the area of the square. But say the other distractors were square numbers also, how could we tell by another means without using Pythagoras Theorem and going through all of that? How could we tell that the answer is 100 centimeters squared without going through that hassle? I think that we should be able to do that. If we are familiar with right-angled triangles, we would be able to tell that if two short sides of a right-angled triangle are 6 centimeters and 8 centimeters, then the hypotenuse must be 10 centimeters. We should be able to tell just by looking. If we know that it is 10 centimeters, square 10 centimeters, we will get 100 centimeters squared. But let us explain. The first and most basic right-angled triangle that we learn is the 3, 4, 5 right-angled triangle. It is so called because the lengths of the sides are in the ratio 3 to 4 to 5. Also, any triangle whose sides are in that ratio is a right-angled triangle. Any triangle with its sides in the ratio 3 to 4 to 5 is also a right-angled triangle. Has to be. Consider the ratio of the two sides of the right-angled triangle that was given. Those are the two sides, 6 and 8. The ratio may be reduced by a common factor of 2. 2 into 8 is 4, and 2 into 6 is 3. So there we have 3, 4. There we see 3 and 4. We may therefore conclude that the triangle is actually 3, 4, 5, but not so fast. It is not every triangle that you see two sides equal to 3 units and 4 units, or the two sides are in that ratio, will necessarily turn out to be a 3, 4, 5 right-angled triangle. Let's say we have a triangle like that. It is possible that the two sides form an angle that is not equal to 90 degrees, 35 degrees. Then you will not have a right-angled triangle. In that event, the third side will not be a hypotenuse. A hypotenuse is only in reference to right-angled triangles and will not be equal to 5 centimeters. So, in the event that the third side will not be a hypotenuse, as we know that the hypotenuse is generally and only in reference to right-angled triangles, then, as long as it is not hypotenuse, then we cannot conclude that it is equal to 5, and it should not be. So there we have our x, and the value of x may be determined by making use of the cosine rule. However, if the two sides are separated by an angle of 90 degrees, and we are sure that they are separated by an angle of 90 degrees, remember, they are two sides of a rectangle. We are sure that they are the two short sides of a right-angled triangle, and the side can only be 5 centimeters long, or it could be the 5 part of the ratio 3, 4, 5. Now, in short, if we have two sides of a triangle 3, 4 are in the ratio 3 to 4, it does not follow that the triangle is right-angled. And it does not follow that the triangle will have the other side being 5 units, or 5 units of the ratio. if the two sides are the two short sides of a right angled triangle, then we are sure that the other side will be 5 centimeters long, completing the ratio. According to the information in the diagram that was given, the two known sides were the two short sides of a right angled triangle because they were also two adjacent sides of a rectangle. So we are sure that the diagonal along with those two sides will form a right angled triangle because they are two adjacent sides of a rectangle. No doubt the other side is 5, and that turns out to be the hypotenuse, like we are going to put right there. So 3 and 4, if those are the two short sides of a right angled triangle, the other side has to be 5. Since the triangle is 3, 4, 5 right, and the actual sides given, the short ones, are 6 centimeters and 8 centimeters, then the multiplier is 2. The 5 side, or side 5, is therefore 2 multiplied by 5, which is equal to 10. So we see that these reduce to 3, 4, which is what we want. But the multiplier is 2. 3 2's 6, 4 2's 8. So the other one has to be 5 2's 10. The area of a square is actually equal to the area of a rectangle. Area of a rectangle is length multiplied by width. The length and width being equal, we usually refer to the length of the side of a square. So we do not usually say the length of a square or the width. We just say the length of a side of a square because all sides are equal. So the area is length multiplied by L, or L squared. The length of each side is 10 centimeters, so we have 10 centimeters squared. I think that what we have done is much of a mouthful, but that is what is necessary to explain the principle. If we can see the ratios immediately, we can make the calculation in our mind, and that will not take more than 2.5 seconds. On the next slide, we will find the length of the hypotenuse of a right angled triangle by making use of the fact that if the two short sides are in the ratio 3 to 4, then the hypotenuse is actually 5, completing the ratio 3 to 4 to 5. In arriving at our conclusion, we have to know which two sides are given, because we cannot interpret the problem outside of the context of the sides that are given. So in arriving at our conclusion, we have to know which two sides are given and make use of them in the correct context of the relevant right-angled triangle, whether 3, 4, 5 or so. Consider the right-angled triangle in which the hypotenuse is missing, the one that we have right there. The hypotenuse is missing. And we see, by looking, the ratio of the two short sides, that's what we're going to be determining. So let us do that. 9 to 12. The ratio may be reduced by a common factor of 3. Into 12 is 4. And 3 into 9 is 3. So 3 into 12 is 4, and 3 into 9 is 3. There we see the 3 and the 4 as usual. We may therefore conclude that the triangle is actually 3, 4, 5. There is no harm in doing that because we already see that the angle separating 9 centimeters and 12 centimeters is actually a right angle. So we know already that is a right angle triangle. Further, we see that the 3 and the 4, the 9 and the 12 are the two short sides. So we may conclude that the other side is 5, which is the longest side. Right. With the multiplying factor being 3, the other side will be equal to 3 multiplied by 5, which is 15 centimeters. Right. And as I said before, we should be able to do that mentally. We should be able to see 9, 12. Reduced by a common factor of 3, we see 3, 4. The other one is 5. 5 multiplied by 3 is 15, and we are done. Arriving at the conclusion is safe as long as we know for sure that the two sides are the two short sides of a right-angled triangle, and we are sure because we have the right angle there. It is said that it is a right-angled triangle, and the two sides that are given are the two short sides. That means they are not equal to the hypotenuse. Neither of them is equal to the hypotenuse. The following are some of the known right-angled triangles that we usually encounter with. In the list, the most popular one is given first and the least popular one last. So we have 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, 25. So those are your very popular right-angled triangles. 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, 25. Right. So when you get problems, sometimes it is good to take a glance and see which category your right-angle triangle falls into. Right. Sometimes they will give you some weird right-angled triangles. Do not force them to be one of those. Just continue to work Pythagoras Theorem and make use of your three most basic trig ratios. So let us see how an examiner may attempt to elude the candidate who is also sharp on his right-angled triangles. So that is what we are going to do. This is how we solve mathematical problem at this level. On seeing the right-angled triangle with one side missing, we immediately use Pythagoras Theorem to find the hypotenuse and make a meal of the problem. Right. What do we mean a meal of the problem? This means that you will not solve the problem in a correct way. Do not use Pythagoras Theorem to find the hypotenuse in every single case, because sometimes the side that is missing is not actually the hypotenuse. Consider the right-angled triangle in which one of the short sides is missing. So the hypotenuse is not missing. So you cannot just jump and use a formula as you would have used it for finding the hypotenuse. Right, some students, as soon as they see the right-angled triangle, they move very quickly. Find the missing side as if they are finding the hypotenuse. And that is just horrible. You need to realize which side is missing and proceed appropriately. So look at the ratio of the given sides. We have two sides, right? 2.5, 6.5, they look weird. Clear the decimal fraction by multiplying by 2. You could have cleared the decimal fraction by multiplying by 10 also. So 10 could have been used. So why do we choose 2? We choose 2 because we are familiar with the popular right-angled triangles, and we are always on the lookout for them. Multiplying by 2 will give us familiar numbers. So if we multiply by 2, so is 2 times 2.5, we'll get 5, and 2 times 6.5, we'll get 13. So 6.5 times 2, 13. 2.5 times 2, 5. So you know that what you have there is a 5, 12, 13. So you know the other side is 12. There we see 5 and 13. The triangle immediately looks like 5, 12, 13. And that is why we have included the 12 right there. The dividing factor is 2. As we can see, from here, divide by 2, divide by 2. So we will also divide 12 by 2. 6 centimeters. Right. Notice that in this particular case, the hypotenuse was given, which is side 13. The triangle is right angled. We are sure because it is said that we have the right angle right here. There is no problem concluding that the other short side is 12. There would have been a serious problem if 5 and 13 were the two short sides. So if what we have right here in this triangle, we have side 5. We know that we are not talking about actually 5, actually 12, actually 13. We are talking about the ratio of the sides. So if what we had right here was a triangle in which side 13, which we know that was given, and side 5 was also given, yet still 13 was not, or the one that is in the ratio of 13 was not the hypotenuse, then we would have a serious problem. As long as we can see that what we have here, side 13 is actually the hypotenuse and side 5 is one of the short sides, then we can conclude immediately that the other short side has to be 12. If not, then we would have had to use Pythagoras Theorem and life would not have been so sweet. On 2 of the previous slides, we have demonstrated the principles and the processes by which we may find the length of a missing side of a right angled triangle. It may be said that the process is not shorter than the use of Pythagoras Theorem. Let us see how it could have been done mentally. Yeah, because what we have done, we have demonstrated the entire thing in graphic detail. So then, the process as it appears on the slide seems to be very time consuming and seems to be very cumbersome. Right? But let us see if we could have done it mentally, which is what we intend to develop. The skills of determining the length of a missing side of a right angled triangle mentally if we know that it is related to the 3, 4, 5, 5, 12, 13, 7, 24, 25, or 8, 15, 17. What process could get the given numbers to resemble one of our popular triangles? If it is, so we have 7.5 and we have 4. What could cause it to resemble one of our popular right angled triangle? Each one looks like half of the numbers in 8, 5, 17, and they really are. 4 multiplied by 2 is equal to 8, and 7.5 multiplied by 2 is equal to 15. Therefore, the other side is half of 17. What we are doing is making use of 2 things. One, our knowledge of the right angled triangles, and of course, our mathematical skills. So we are searching for one that is familiar. Of course, by looking we see 4, we see 7.5. If we multiply these by 2, we get 8, we get 15. So we could say 8, 15, 17. Right, we could investigate for 8, 15, 17, and of course we are spot on. Therefore, the other side is half of 17. This is half of 8. This is half of 15. The other one is half of 17. Half of 17 is 8.5. Right, that's all there is to it. As in every single case, we need to ensure that the side that we are claiming to find is actually the one that is missing. For argument's sake, if 2 sides of a right angled triangle are 7.5 centimeters and 4 centimeters, it does not follow that the other is 8.5 centimeters. It is going to be 8.5 centimeters only if it is the hypotenuse that is missing. Right, so if it is the hypotenuse that is missing, we can come to that conclusion. The side can only be 8.5 centimeters if the 2 sides given are actually the 2 short sides, right? As we have them right there. If the hypotenuse is missing, it will be 17. If for argument's sake there is a right angled triangle and 2 of the sides are 8 and 15, the other side is not automatically equal to 17. It will be 17 only if the missing side is the hypotenuse. Right, so say for argument's sake, we have 7.5 for the hypotenuse and 4 for the short side. The missing side will not automatically be 8.5 centimeters because we cannot have one of the short side, 8.5 centimeters, being longer than the hypotenuse, 7.5 centimeters. Right, so we will have to take another approach. So we also need to be cognizant of the side that is missing when we are trying to get that into one of our templates, that it is placed in our template with the missing sides in its appropriate place and the sides that are given also in their appropriate places. There we have another one. Multiplying the sides by 10, we will clear the decimal fraction, but the resulting numbers are not any of the basic sides. However, this does not prevent them from being a part of the popular right-angled triangles. In fact, they are. So what do we do then? After multiplying by 10, the sides will have to be reduced by a common factor of 5 in order for us to see that the triangle is actually 3, 4, 5. Multiplying by 2 immediately causes it to be obvious. So 1.5 multiplied by 2 is 3, 2.5 multiplied by 2 is 5. We have sides 3 and 5. The other one is therefore side 4. Can only be side 4 if it is actually one of the short side that is missing. 4 divided by 2 is equal to 2. The other side is 2 centimeters. These simple calculations can be done mentally. We still need to be careful that after we have decided that it is actually side 4 that is missing, that the missing side is actually one of the short sides. If it were the hypotenuse that was missing, we are sure that the triangle could not have been 3, 4, 5. One short side is missing. Side 4 is actually one of the short sides. We have no alarm. Which of the following sets has an infinite number of members? There are many ways of defining an infinite set. All definitions are given in direct or indirect reference to its opposite, which is the infinite set. Some ways of viewing a finite set are: in naming a finite set, the list of elements must come to an end. So as long as the set is finite, the list of elements must come to an end. A finite set has a definite number of elements. The number of elements of a finite set is bounded. The infinite set will therefore have the characteristic that will be the opposite of those of the finite set. The list of elements in an infinite set has no end. An infinite set has an indefinite number of elements. The number of elements of an infinite set is unbounded. In discussing the options, we will give examples of finite and probably a single example of an infinite set. If we attempt to list the odd numbers between 0 and 20, the list must come to an end. The set is finite, so we are of course looking at option A, odd numbers between 10 and 20. If we attempt to list those numbers, odd numbers between 10 and 20, the list must come to an end. The set is finite. And those odd numbers between 10 and 20 are 11, 13, 15, 17, and 19. there you have the list of odd numbers between 10 and 20. It starts at 11 and ends at 19. It is finite. We may also list all of the prime numbers between 10 and 20, which is of course option B, prime numbers between 10 and 20. Those prime numbers are 11, 13, 17, and 19. As we have shown, it is possible to list all of them. This makes the set of prime numbers between 10 and 20 finite. We can list all of them. It will come to an end. It is finite. A factor of 20 is a number such that 20 is divisible by it. We may also say that the number may divide into 20 without leaving a remainder. Some factors of numbers that are sometimes neglected are 1 and the number itself. So in the list of factors of 20, we will be careful not to leave out 1 and the number itself, which is 20. 20 will go into 20, no doubt. So there we have the list of the factors of 20. Based on the two previous examples, it should not be difficult to see that the set of factors of 20 is also finite. No problem with that. Multiples of 20 are the result of multiplying 20 and another natural number. So we have them right there. 20, 40, 60, 80, etc. Up to 200. And as we have shown, it will continue and continue on and on and on. Hopefully, we will not need to list another 100 for you to realize that the list is endless. This is therefore an infinite set. Option D is correct. So I hope that we need not include 100 elements for you to realize that this set will be infinite, because after including another 100, we will see that we would not have exhausted the list, and we will continue as before. Number theory is most times neglected by teachers, and I am not innocent. I usually take advantage of the fact that the topic is presented at the lower grade levels and also in primary school. Further, I integrate it when relevant into the other topics. So I do not neglect it all entirely, but we do not focus so much on it and try to develop it from scratch. Of course, which may be a fault in my presentation of mathematics that I might need to address in a short while. I'm just taking advantage of the fact that number theory is presented in the lower grade levels, and at times when relevant I integrate it into the other topics that are being discussed. The set of odd numbers between 10 and 20 is bounded by 10 and 20. This is one of the reasons why it is finite. However, not every bounded set is finite. The set of fractions between 0 and 1 is bounded by 0 and 1, but it is not finite. Let us take a look at a class of such fractions with a numerator of 1. Now, between 0 and 1, we have many fractions. We are just taking one class. We are just considering those that have numerator of 1. And we have it right there. A half, 1/3, a quarter, 1/5, 1/6, right up. And we will see that it is infinite. Although it is bounded, it is still infinite. As you can see, the denominators will continue indefinitely. The set is therefore infinite. The denominators are increasing in size, therefore the fractions are decreasing in size. So if we are going to list all of these fractions or attempt, we will increase to 1/7, 1/8, 1/9, 1,000, 1,000,000, 1,000,000,000, and we'll continue on and on indefinitely. So that although it is bounded, it is still infinite. The interest rate on investments in a bank decreased from 8.5% per annum to 6% per annum. What is the difference in size of the annual interest on a deposit of $2,000? This problem is just another way of writing problem number 21, if you can remember problem number 21. We may therefore use a method called solving by analogy to solve it. In this method, we use the similarities that it shares with 21 and progress similarly. The differences, if any, will be given different treatments. So when solving by analogy, we solve a problem of a similar nature by making use of the similarities. So we are going to make use of a problem that we have solved before that has similar characteristics. And in the case that they are similar, we will continue in a similar way. But in the event that there are some differences, we need to progress treating the two problems at that particular point, or in those particular cases we will have different treatments, or we will treat the problem that we are solving presently in a different way. The only significant differences are the figures. Everything else is pretty much the same. We will begin by subtracting the percentages as usual. Of course, as it is said, only the figures are different. And of course it is coined, the problem is coined in a different way. So we have 8.5 minus 6 and we have 2.5%. So let us now find 2.5% of 2,000, which is written like that. We may do this mentally by saying 2,000 divided by 100 is 20. Then multiply 20 by 2.5. So we have it here. 200 into 2,000 is 20. Multiply 20 by 2.5. So 2 times 20 is equal to 40. And a half of 20 is 10. So we'll put the 40 and the 10 together. 2.5. 2 times 20 is 40. Half of 20 is 10. So we have 10 plus 40. And when we put them together, we get 50. So we are sure that our answer is $50. And that is represented by option B. Same problem. The problem may be solved again like we did in 21 by finding the two percentages of $2,000 and subtract the results. Right. So again, 2,000 divided by 100 is 20. So we will say 2,000 divided by 100 is 20. 8 times 20 is 160, and a half of 20 is 10. 160 plus 10 is 170. And we'll do the same here. Just we do not have a fraction, so we just say 6 multiplied by 20 is 120. So we will have 120 on that side, 120 there, 170 on the other side. We just do the subtraction, we get $50, and that's all there is to it. The first method seems to me to be a little less cumbersome. I will therefore recommend it, but as they always say, make your choice. All of them are nice. How many liters of water will a container whose volume is 36 centimeters cube hold? In solving this problem, we need to make use of the fact that 1,000 centimeters cube is equal to 1 liter. So let us first write the relationship in a ratio. We are going to be using ratios to solve the problem, and the relationship is what? 1,000 centimeters cube is equal to 1 liter. Right. The volume that we have is 36 centimeters cubed. We do not know its equivalent in liters. Let us call it x. So on the centimeters cubed side, we'll have 36 centimeters cubed, and the volume in liters we'll just have x because we do not know what it is right as yet. As we see in the first ratio, we're just using some analysis. As we see in the first ratio, the figure on the centimeters cube side is larger. Of course, it's obviously larger. We have 1000 here, we have 1, right? So the figure on the centimeters cube side is larger than the one on the liter side. We need to maintain that principle. The figure that we have for x must be smaller than 36. We will therefore divide 36 by 1000. So we have a large number here, small. What we need here is to have the same thing happening. The one that we have on this side is large and the one on this side is small. We therefore achieve that by dividing by 1000. And of course, we have other ways of using the ratios to solve problems that we have in the presentation of the multiple choice practice papers. And we have seen quite a bit already, and no doubt we'll see quite a few coming again. But in this particular case, we are just using a simple analysis. On the left hand side, the number is always larger. We want a figure that is supposed to be on the right hand side. It is to be smaller than its counterpart on the left. We will therefore divide by 1000. Right, and by dividing by 1000, we are reducing the figure by 3 places of decimal. The smallest infant knows that dividing by 1000 is reducing the number by 3 places of decimal, and we achieve that right there. The answer is option A, 0.036 liter. The problem should have had a distractor that is designed to catch the candidate who will multiply instead of divide. Multiplication would have given 36,000. It was not included as one of the options. If a candidate multiplied by 1000, he would have realized that the option is not there. He will have no choice but to divide by 1000. And in the end, it turned out that he did not have to do much work, much thinking, or anything. Because if he's going to multiply by 1000, he will get 36,000. It is not there. What he will do is divide by 1000. And the answer would have been there. Unless it is in anticipation by having option D, 3600, that the candidate will multiply by 100 instead. Well, I'm just thinking that the student or the candidate would have been at least cognizant of the fact that 1000 centimeters cubed is equal to 1 liter and not necessarily 100. But stranger things than those have happened before. What is the frequency of the median weight? What is the frequency of the median weight? The median weight is the item of weight that is in the middle of the data. The median is always the middle. Let us identify the item that is in the middle of the data. So, find the item that is in the middle. There are 9 bars that represent 9 different weights. Like we can count them with those nicely decorated numbers. Black, red, and gold. The colors of Richard James Mathematics Resources. 9 divided by 2 is 4.5. We have 9 of them. The median bar is bar 5. Let us take a look at its associated frequency. So we have bar 5 there. Right, so let us take a look at its associated frequency straight across from the top of it, and we have 12. Good. The correct answer is option C. How many packets were weighed? We need to know the number of all of them that were weighed. Remember that the mean is equal to the summation of fx divided by the summation of f. The summation of f is the total of all of the entries, because when we are finding the mean, basically when we are using a basic form, we divide by the total of them. So it is the summation of all of the entries, and we divide that by the number of entries. Therefore, the summation of f is the total of all of the entries. To find the total number of packets, we will therefore find the sum of the frequencies. Sum of the frequencies will be equal to the total number of them. We will proceed by adding the frequencies associated with the different bars. So find the frequency associated with the first bar. First bar is at 2, as we can see. Right, that's a little playful. Then the second bar is at between 4 and 8, exactly 6. Then we have the 8th bar. Then that one exactly between 12 and 16, 14. We are going down this time to 12. Then we will have between 8 and 12 we have 10. And then we have 4 bars. There are 2 bars that are on the same level. Right. And then finally, although this bar we have right here is on the same level of this, we have included that one already. So just 6. After, we may add all of them, and the result is 66, and we have that as option C. So that is represented by option C. What is the modal weight? In any data set, the modal score or item is the one that occurs the most times. It is therefore associated with the highest frequency, the one that occurs the most time, the one that has the most frequency. That is the one that is the modal weight, or the mode. The highest frequency is represented by the tallest bar. We need the associated weight. That is our tallest bar, and there we have it pointing down right there to the associated weight, which is 10.1 kilogram, and we have that for option B. That is the correct answer. Right. A rectangular sheet of paper measures to the nearest centimeter 6 centimeter by 9 centimeter. What are the least possible values of its dimensions? Although the solution of this problem is really very simple, it is based on some serious principles. We will first look at what we mean by the nearest centimeter. The figures are given in centimeters. Considering that there is no fraction of a centimeter, the smallest place value is therefore centimeter. Right, so we are going to put in some place values right there. Right there. The nearest centimeter implies that the figure may have been rounded off. So the nearest centimeter implies that the figure may have been rounded off. The question is therefore asking for the smallest numbers that can be rounded off to 16 and 19, the nearest centimeter. Let us focus on the place value that we are concerned with, which is the nearest centimeter. So the centimeter place value, we focus on that one. The figure would have had to be rounded from the very next less significant place value. The figure would have had to be rounded from the very next less significant place value, from that one. Right. So if we are rounding a number, we generally round from the next significant place value. So we are at centimeters, we need the next significant place value. Consider the number that we are rounding to 16. So we are going to go to the actual values that we have right here. We have taken a look on the previous slide on the illustration of the place values and the one that we are rounding to and the one that we are rounding from. Now we'll apply that to the particular numbers that we have here. So we are going to be taking a look at 16. 16 centimeters of what? 16 centimeters, we have the centimeter place value and we have the tens of centimeter place value. Exercising our familiarity with rounding numbers, if we want the smallest number that 16 was rounded from, it would have to be related to 15. So 16 rounded from a smaller figure, it will have to be related to 15 in some way or the other. As before, focus on the place value that we are rounding to. That is the one that we are rounding to. The figure would have had to be rounded from the very next less significant place value, the tenths of centimeters, which is the one before the one of less significance. For 1 to be added to 15, the next place value needs to be 5 or more, because if it is 4, we generally neglect it. If it is 5, 6, 7, 8, or 9, we accumulate it. So it will have to be 5 or more. So the least one is a 5 for the next place value. By analogy, the smallest number that 9 may be rounded from is 8.5. So the correct number is option C. So the correct answer is option C. So one is 15.5 here and the other will be 8.5 right there. The problem may have been solved in a few seconds. My explanation needed not take so long. I opted to include all of the principles involved in solving the problem and more. In the case that the next one that you are required to solve is not so straightforward. So that is what I'm doing. I'm including everything that we need to consider just in case the problem is not just one like that, as simple as that. Because sometimes the problems that are based on particular principles are sometimes coined and recoined, sometimes adjusted, readjusted, designed in such a way that only the alert person will go through this problem successfully. So right here, I'm just including all of the principles that we need to consider in order that we will be able to handle a wide variety of circumstances. AB is parallel to CD and angle BAD is 32 degrees. Angle APC is equal to, we need to find angle APC. What do we do? First, of course, we are throwing in some highlights for some of the line segments that we have. AB is parallel to CD, as it is said. AB is parallel to CD. This causes angles BAD and ADC to be alternate, or what we call Z angles. So that causes ABD and ADC to be equal Z angles, alternate angles. There we have them. Now, if two angles are subtended by the same arc, and in this particular case it is AC, so this arc is AC. If two angles are subtended by the same arc, the one at the center is twice the one at the circumference. This causes APC to be twice ADC. So there we have them. The one at the center is APC. The one at the circumference is ADC. The one at the center is twice the one at the circumference. This is 32. This one is twice 32. So angle APC is equal to 2 times 32, which is equal to 64 degrees. The correct answer is option B. Because of the parallel lines, in addition to the angles that are subtended by the same arc, there are many things that we may consider in order that solving the problem may be simple. Angles BAD and BCD are also equal. BAD and BCD, they are equal. So we have this one, BAD is equal to BCD, because these two angles are subtended by the same arc. Right, so this is the arc that we are talking about, and we have this angle is subtended by the arc, and we have this angle is subtended by the arc. So are angles ABC and ADC. ABC, ADC. This is the arc that subtends the two angles ABC and ADC, or we may say that they are angles in the same segment. So they are equal, 32 degrees also. Where two lines intersect, opposite angles are equal. So APC is equal to BPD. So APC is equal to BPD because these two angles are opposite to each other on intersecting lines. Right there. You could have taken other approaches to the solution of the problem that are based on these facts. So you could have taken another approach to solving the problem which makes use of these facts. I'm just including them so that we are aware. Life is simple, or the entire situation is simplified by the fact that these two lines are parallel to each other.